Okay, so I've started the recording and I will quickly share the content. So I hope you can see the whiteboard now. Someone can verify that? Yeah, okay. So the concept of PIV we will discuss once again. So what is the PIV? So PIV is peak inverse voltage. Peak inverse voltage means we should not go beyond this voltage in the reverse bias mode of the diode. If we go beyond this voltage in the reverse bias, then what would happen? Then the diode will go into the breakdown region. So this much I hope you understand. So what should be the voltage in the reverse bias? We need to calculate. So whenever we are given a circuit, we need to calculate what is the maximum reverse bias voltage that is coming across the diode while operation in this circuit. The maximum reverse bias voltage that is coming across this diode while in reverse bias condition, that voltage must be lower. That voltage must not cross the PIV. That voltage must not cross the PIV. Okay, so this I hope you understand. Now you see, so we had calculated in this particular configuration, in this half wave configuration, we calculated that during the reverse bias case I is 0. So here the voltage is 0. That means this PIV voltage is same as Vm. Okay, and you see the direction of the voltage is also given as the reverse bias case. So the maximum voltage can be the maximum amount of this particular voltage that is in the input side, and that we know is Vm. So your PIV must be more than Vm. So in magnitude it should be more than Vm. Okay, and in your data sheet and in any other case, if we write in this manner that PIV is greater than Vm, this directly has the meaning that we are talking about the magnitude. However, if you want to be very precise, this voltage, this inverse voltage is actually a negative voltage. Okay, so it is a minus Vm, and hence PIV, that value should be less than minus Vm. So it is for more precision from the mathematical point of view, but for our standard engineering purposes we can understand it in this way, that PIV should be greater than the Vm. Here what is Vm? It is the maximum reverse bias voltage across the diode in the circuit. Someone open their mic, wants to say something. Okay, so PIV greater than Vm or greater than this, should be greater than this voltage, greater than or equal to. Okay, then this particular maximum reverse bias voltage across the diode in a circuit. So what we need to calculate to obtain the PIV? We need to know, you need to calculate this you can calculate from the circuit. You can calculate the maximum reverse bias voltage across the diode when it is in operation in the circuit. So this voltage is actually the PIV rating. So the PIV must be more than this voltage. Okay, that is what we say in engineering terms. Now with this idea, so what we need to, when we need to calculate the PIV, what we need to do? The diode whose PIV we need to calculate, we need to set it in reverse bias condition. So in this case, you see in the left hand side, so suppose we are calculating the PIV of these diodes D1 and D2. So suppose it is in this operation when the D1 is reverse biased, then what happens? When D1 is reverse biased, then you note this particular circuit here which is absent. In this place, what is there actually? you can appreciate me drawing this. So in the secondary side, in the load side, what had happened, we have a negative and a positive source. So this is the source here, and then we had a diode which is now open circuit, and here we have a resistance, the load resistance RL, whose positive side is voltage, positive side is this, and negative side is this. Correct? Do you appreciate this? Anyone has any doubt or not able to understand why I have drawn this particular diagram? So the maximum here, it is Vm, and when this is Vm, you try to understand what is the voltage across the load resistance. Here also we are getting Vm, and this voltage is coming across the load resistance. So the voltage across the load resistance is also Vm, the peak voltage in the secondary side. Okay. So what is the voltage appearing here? The voltage appearing here, reverse bias voltage, is, let me call this VR, that is 2 Vm. When it is reverse biased, that means the polarities should be drawn like this. When I draw the polarities like this, the value is 2 Vm. Okay, because you apply the KVL, you will directly get this. So this is nothing but the PIV. So PIV should be greater than this VR. So here PIV, so normally we write the equal value, equal level we write. So it is not 2 VP, not VP, actually this should be 2 VP. So this was the correction that I wanted to make. This should be 2 VP. In this side, this should be VP in this configuration. Why? Let us note this circuit. So let us try to find out the voltage appearing across one of these diodes. Suppose this one. So what is happening here? You see that this is the VP. We try to see the circuit which is now open, this part. Okay, so the circuit, if we draw completely, it will be like this. So here the transformer secondary side is coming, then you will have an open circuit here. There is a diode, D1 diode is here, then you have the resistance, and then you have another diode here, and this is coming here. So this voltage is Vm with the polarities as shown. What is the polarity across RL? Here it is plus, here it is minus. And what is the voltage appearing across RL in this particular situation? That is also Vm. Okay, now these two diodes are here. Okay, two diodes are here. And hello, someone trying to say something? Hello, please put your mic off. So please be careful not to switch your mic on accidentally, because it disturbs the session going on. So please be careful about your mic, and unless you want to say something, please be careful not to switch your mic on. So in this situation, what happens, you have two reverse bias voltage, two diodes actually. So the total voltage that is coming in the circuit which must be balanced by these open circuits, that is 2 Vm, but there are 2 diodes in this case and both are reverse bias, so we have the voltages, see, not this, sorry, this should be minus plus, here it should be minus plus VR. So if VR, so you see VR must be equal to Vm in order that this voltage in the circuit is Vm and this Vm voltage in the circuit can get balanced out, because there is no current flowing through this circuit, so these voltages must balance out. So your VR should be equal to Vm and PIV is Vm. So the PIV is the peak voltage. It is simply VP out or Vm, as you can see that. So I hope you understand this. So there was a mistake last yesterday about the PIV of these two configurations, so that is clarified now. So I move ahead. So we have got in the rectifier, we have got these pulses. So we have got as the output also some pulses. We have not got the DC voltage actually. So to get the DC voltage, we need to use a filter. So there are various types of filter, and the most basic one is to just use a capacitor. So you could understand that if we use a capacitor in this place, then what happens during the diode being forward bias, this capacitor would charge up to a value of Vp. So you see the value of Vp, capacitor is charging up, and when it goes lower than Vp, that is it is less than Vp, this input side voltage, then this capacitor has no place to discharge, because the diode will act as a reverse bias condition in that case, and hence there will be no current in the circuit. So the capacitor stays in Vp, stays in the voltage of Vp. So in this situation, this Vp will be constantly maintained in the output. So you get a very nice DC voltage in this case. Okay, so this is one configuration in which you can get a constant DC voltage of value Vp. So please note the value also here. It is not 0.318 Vp, but it is Vp directly. However, this sort of configuration is not like it cannot happen in practice, because we know that the capacitance is not a pure capacitance. It has some resistance along with it in parallel. So you can see this configuration in the right hand side. So what would happen? What would happen is that during the reverse bias condition, there will be, or during the condition when the diode is reverse biased, of course this particular circuit is off, but this particular circuit will have some flow of current. And if we can make this RL quite large, then the time constant, the filter time constant, which will dictate the also the discharging time constant, will also be pretty large. So the discharge will happen very slowly, but in any case there will be a discharge, so this voltage will be falling down a bit from the value of Vp. So this line, which appears almost straight, so because of the picture in the book, but this line is actually not straight, so much straight, it is like this. So some ripple is there. Okay, so it should be like this. So this is what happens with a loaded this is a loaded capacitor input filter, and the output is DC current with small ripple. And if we if you apply this capacitor filter at the output side of the full wave rectifier. So what we are trying to do is, instead of simply having a load resistance connected at the output, we are suggesting that the load, in this first case we are suggesting that the load resistance be replaced by a pure capacitor, and we saw that what improvement we can get. In the second case, but since this is not practical, now in the second case we are saying that add a capacitor along with the load resistor. So the load resistor was already there, we added a capacitor here. What would happen? We would get a ripple voltage, small ripple voltage we will get, and the nice DC, almost DC voltage you will get here. Okay, so this is also a configuration where you will get DC voltage. Now after we completed this, we have another very typical circuit, which is the clipper circuit. In clipper circuit there are two very distinguished type of clipper circuits. One is the series and another is the parallel. Very easy configuration wise, it is very easy to remember. What is happening in the series circuit is that the diode is just after the voltage source. The diode here is just after the voltage source. Okay, and this is an additional DC voltage which can be present in a circuit or may not be present also in a circuit. So it is actually, it may be also absent. So if it is absent, you can understand that this becomes a half wave rectifier. If this 5 volt was 0, basically if this battery was absent, this would have become a half wave rectifier. So half wave rectifier is also a clipper circuit. What is the meaning of clipper circuit? That we should understand first, so that we can easily identify from the output behavior of a circuit whether it is clipper or not. So in a clipper circuit, the input voltage waveform is clipped while maintaining its shape. So some part of the voltage waveform is clipped off, simply clipped off or cut off, you can say. Rest of the voltage waveform's shape does not get affected. These type of circuits are called clipper circuits. As you can appreciate now that the half wave rectifier is also a clipper circuit, because the negative side is clipped off in that case. In the half wave rectifier, the positive side of the sinusoid is kept as it is, but the negative side of the sinusoid is clipped off. Is the full wave rectifier a clipper circuit? Can anyone answer this? No, because there is no clipping of the voltage waveform. There is a transformation of the voltage waveform. There is no clipping happening. So with this idea of the clipper circuit, we try to analyze two different types of clipper circuits. First is the series one, which is like this, and this is an additional DC battery. You will often see in diode circuits that along with AC, DC source is also present. So how to analyze these things? First thing to analyze any circuit, so we are again going back to the basic principles. We will always start from the basic principles of analyzing a diode circuit. The first step is to understand whether in which situation the diode is forward biased and in which situation the diode is reverse biased. When we clearly identify, clearly are able to distinguish these two regions of operation, then in the forward bias region we apply a certain approximation which fits well. Normally the ideal approximation is perfect. Sometimes we also replace it by the knee voltage. Very rarely we use the knee voltage with the additional resistance of the diode. Very rarely we use that, but that is also can be used. and in the reverse biased it is an open circuit, the diode is open. So these two situations we need to analyze. So the first important thing to analyze is in which range of this input voltage is the diode forward biased and in which range is it reverse biased. So as you can understand, we always start and you start practicing drawing this sort of input output waveform diagrams. So this is the input with the time. So this is Vi, this is V0. So Vi is 20 volt peak to peak. So we have a होगा, लेकिन let us go step by step for everyone. So it is, I am trying to draw the sinusoid to the best extent possible. So anyway, so here it is 20, here it is minus 20, plus 20 minus 20. Okay. So we start the analysis from the zero of the sinusoid. So when this voltage is 0, what is the voltage faced by the diode? It is plus 5 volts. So it is on. It is in on condition. How long will it be on? You can understand this would be on as long as the voltage across the diode is not getting 0. So if this is like 5, and so when the voltage in the AC source is minus 5 volt, somewhere here, only then the diode will become reverse biased, or it will become off beyond minus 5 volts. So above minus 5 volts the diode is on, below minus 5 volts the diode is off. So in this input voltage you can actually demarcate a region where the diode is on and off. First thing is to do this. The region, what I already told, the region of the forward bias operation and the reverse bias operation needs to be clearly identified. This is the first step. So the range of values of the input voltage where the diode is forward biased and the range of values when it is reverse biased. When this is clearly identified, now we apply one of the approximations, and we apply the ideal approximation if nothing is told to us. Then if this is ideal approximation, then this is short, and when this is shorted, we need to also know what is the output voltage we are talking about. We are talking about V0 here. This is the load resistance. Normally we talk about the output voltage across the load resistance. So what would be this V0? V0 would be Vi plus this. V0 would be Vi plus the 5 volts. Okay. And that is nothing but this entire region, because whatever voltage is in this side, that comes at the output. So the voltage in this side is this whole thing added with a 5 volts. So if you add a 5 volt to this region, what is basically happening, what is happening, you try to understand that you are having this minus 5 volt as the 0 level in the output, and the entire input voltage is getting redrawn in this side. So you are having this minus 5 volt as a 0 level, and with this 0 level you can redraw this input voltage in the on region, that you can redraw. So you will have something like this. here. This is 5 volt. And again in the on region here, this is one time instant and this is also another time instant where the intersection has happened here. So from here again you are getting the sinusoid and till here, till the next. Yes, so the on region we are very easily we can draw. We just simply redraw this by shifting this signal 5 volts upward. What happens to the region where it is off? Obviously when it is off, we don't have a current flowing in the resistor. That's why V0 is 0. So this is what is happening here. So you see now how the input voltage has been clipped off. So this was a waveform that was coming, but now it is simply clipped off. And a 5 volt we have also, like, it has got a bias actually of 5 volts to the upside. So in this way, in the generic way only, you need to analyze each and every different clipper circuit that you will be given to solve. Okay, you cannot have ready solution for each and every clipper circuit. You have to see the circuit and you have to analyze. But why we are doing this analysis exercise? Just to get you more familiar with how the steps are involved, how I am doing it. You also, as more and more you solve, you will get get more practice. You will take lesser time to solve, and it will benefit you in the during the examination purpose or in the tutorial purpose. More and more you solve, it will become more and more easy for you to solve a new diode circuit. So let us solve this one, the parallel one. So here also we would draw the input output voltage wave. So normally you will be asked to draw this. Okay, so let us draw this. This is the input side voltage, 20 volts, 20 minus 20, sorry, Vi, there it is, V0, and here what happens, here you see this 4 volt has a positive side here in this side and negative side in this side. So as long as the so when this diode is forward biased, that is our first question. So here it is, as long as the input side voltage, when the input side voltage is 0, of course it is forward biased. When the input side voltage reaches 4 volt, till then it is forward biased. After it reaches 4 volt, it goes past 4 volt. What happens? This diode becomes reverse biased. So there is a 4 volt cutoff place here, and below, when this voltage is below this 4 volt, always the diode would be forward biased. So this is the on region and this is the off region. This is demarcated, and now you have to simply redraw the voltage by taking the 4 volt line as the 0 line in the output. So what happens now, this is the on place is here, so we also have this intersection times. this much is on, rest was off, and then again we are having on from here till here. And then we are having off, again we are having on. So this is the output voltage. So does this make sense? Anyone has any confusion or anything? I hope it is fine. Okay, I had not taken the bias at 0, so that is something I did not do correctly. So this should be shifted 4 volts downwards, because the output so we are trying to draw the V0. V0 is here. This is the V0 when the diode is forward biased. So it should be like this, current flowing in this direction. So in that case you will have, this is first 4 volts, till 4 volts we are having the current conduction, and this voltage at 4 volts is 0, so it is here. The voltage at 4 volts is 0 here. Below that you have the current conduction. This would be the shape. Fine with this. So there can be lot of different such circuits. Yes. Okay. So this is just the name of the configuration. Here you see that the diode is, so it seems like it is in parallel with the voltage source. So it doesn't come just after the voltage source. So that's why it is called parallel. So it looks like it is in series, though both these are in like a series circuit, but the name is given in this manner. So it is just the name given, so I cannot really explain in much more elaborate fashion. Though both these are series circuit, I understand this, but here it seems like just after the voltage, the voltage source, the diode is here and the resistance is in parallel, and that's why this is called the series one, and here the diode is in parallel with the voltage and it is called the parallel. I think that is the reason. I'm not very sure why it is called so, but this is the name given. So you don't need to worry about the name. You just don't worry yourself with the name. Names can be anything, but it is just a circuit and you have to analyze the circuit, that's all. So any circuit you are given, you should be able to analyze. The first thing that you need to understand is the region of the input voltage for which the diode is forward biased and for which the diode is reverse biased. Once you identify that, you need to then see the output voltage in that forward bias region and in the reverse bias region. Remember, the output voltage is not the voltage across the diode. It is a voltage across the load resistance for most purposes or for most problems that you will face. But the V0 can be set anywhere in the circuit. So it depends on how the question is set. Okay. So that is the thing. So this is the clipper circuits. There is something called the clamper circuit. So I will just give you some quick variations of these clipper circuits for you to solve on your own. So one thing you can do, So this type of combinations you can try. You try to reverse the DC battery voltage. Try to reverse the battery voltage in both these diagrams. This is one set, one another combination you can try to draw. Reverse the direction of the diode in both these problems. In both these numericals, reverse the direction of the diode. Both you can try together. So reverse the DC voltage as well as reverse the diode. Reverse the DC voltage as well as reverse the diode. And then you try to solve. So all these different combinations, permutations, combinations can be tried, and different circuits will get formed, and different outputs will also get created. Now about the clamper circuit. So let me try to remember the clamper circuit, how it was configured. Yes, so this is the clamper circuit. So I will draw the clamper circuit. The clamper circuit has a AC voltage. There is a capacitor. The clamper circuits will invariably contain a capacitor. Okay. Then there is a something came up. Diode. And this diode can have a DC voltage along with it or not have a DC voltage along with it. So let us take the case where it does not have a DC voltage. Then what happens? So this is having some value, suppose 20 volts peak and peak. So there is a lot of disturbance in the writing pad today. 20 volt peak to peak. Why all this is coming? And this is the ideal diode. Suppose this is RL, some resistance, and we need to check the voltage. Check this voltage V0. This is Vi. Okay. What happens? You try to understand. When the diode is, when this voltage is in the positive cycle, then there is no conduction through the diode. Okay. So in the negative cycle, we start with the negative cycle here, the analysis. In the negative cycle of the diode, what would happen? Sorry, in the negative cycle of the input source, what would happen? The diode will be forward biased. In that case, it will have a current drawn here in this loop. There would be a current flowing in this loop during the forward bias condition of the diode, which happens in the negative half cycle of the input source. In this situation, what would be the voltage that would be created across this capacitance? The direction of the voltage will be this, and the value of this voltage will also be 20 volt. 20 volt. It is not peak to peak, it is 20 volt. Next, when we have the positive cycle, the next positive cycle, then this voltage, this diode will become off that time. When it is when in the next positive cycle, this diode will become off completely. What would happen? The voltage V0, the voltage V0 will then become this voltage plus this additional 20 volts. right? And you also notice that this diode will never become forward biased in the circuit again. So once it has become forward biased and charged this capacitance to 20 volt, after that, for all voltage Vi from 0 to plus 20, of course this remains reverse biased. For 0 to minus 20, so only at minus 20 the voltage across the diode becomes 0, but with that voltage it is not able to conduct anything. Okay, so at all parts of the all instants afterwards, this diode will remain off once the capacitance is charged. However, what happens to the voltage, output voltage? This output voltage will be exactly equal to Vi plus this 20 volt. That means the output voltage will have a bias of plus 20 volt. So if this is 20 volts input, the output will have a bias of plus 20 volt added to this input signal. The output so it will go from 0 to 40 and to rise from here, and noting this, times should be same. So this is what happens in a clamper circuit in general. The waveform, the input side waveform remains undisturbed, unchanged. Only the bias voltage or only the level of the voltage is changed. So the level of the voltage means, so here you can understand this input voltage has an average value of 0, but in this output voltage is also the same signal, same AC signal, but the average value becomes 20 volts now. So there is a level shift in the output voltage. So this level shifting is called clamping. It is as if you pull up or pull down the alternate signal. You pull up or pull down the sinusoidal signal and clamp it to some level. So that is why it is called a clamper circuit. All clamper circuits will have this sort of behavior. All clamper circuits will have this sort of behavior. Okay. So now let us see another clamper circuit where we introduce a battery voltage and also try to reverse the direction of the diode. Two things we will do together and we will do the analysis very carefully. One has to do the analysis very carefully in these cases. Please keep that in mind. Don't hurry, don't worry. Just keep doing things step by step and you will be able to get the right answer. So we have designed the circuit this manner. So as you can understand, the exact value of C and RL doesn't really matter as long as this RL is quite high. So why we need this RL to be quite high? I leave it to your understanding. So you should be able to give answer to this on your own. We already discussed something about time constants and all. So that is the reason why this RL needs to be very high. So let us again take this particular 20 volt peak to peak and perhaps this is suppose 5 volt. Then what would happen? in this case. As you can understand, the diode will be forward biased only when this voltage has exceeded 5 volt for the first time. So for the very first time, of course, there is no voltage across the capacitance. So when we start in the positive half cycle, this capacitance is like a short in that case, because there is sinusoidal voltage passing through it. It acts as a short to the sinusoidal voltage, we know this. So unless this input voltage crosses plus 5 volt, the diode is not getting forward biased. After it crosses plus 5 volt, then the diode is forward biased and it is a short now. Now it is a short. So when this is a short, then there is a current in this circuit. Okay. And when in this current will charge up this capacitor, to what level it can charge up this capacitor? The maximum voltage that can happen here is 20 volt. There is a plus 5 volt here. So during the forward cycle, 20 volt, 5 volt. So what would be the voltage here? It would be 20 minus 5, which is 15 volt, and the charging would be like this, 15 volt. Okay, I hope I have drawn everything correctly. Voltage directions, yes. So this should be 15 volt. Okay. Now in the negative half cycle, what happens, or what happens when we are again below 5 volt? Yes, when we are again below 5 volt, so this voltage will keep alternating. So this phenomenon happens after 5 volt. So again the value drops below 5 volt in this region, and in this entire region it is below 5 volt. What happens in this entire region? When this is below 5 volt, the diode is off. When the input voltage is below 5 volts, the diode is off. The charging has taken place completely. During this region, the charging has also taken place, and now you see this voltage is always present there, because the discharge will not happen. Discharge circuit is this one. The discharge is not going to happen because the RL is quite high. So the discharge time constant is very low. So you can say that this voltage across the capacitance will remain as it is. So this minus, so this 15 volt in this particular polarity will always be here across the diode, and this plus 5 volt will always be here. So you can see that the diode will be facing a reverse bias voltage now, and this would further like we have to analyze along with this VI now. So this voltage is minus 15 volt here. When this is 0, this is minus 15, and this is plus 5, so minus 10 here. So you have to increase this voltage, and when this is 10 volt, then 10 minus 5 is 10 minus 15 is minus 5, and the voltage across this would be minus 10. Still it is reverse bias, so we need to have this voltage more than 5. So only when it is 20 volt you will have a plus 5 volt here, right? When VI is 20 volt, only then this is 20 minus 15 and you get a plus 5 here, and which is able to make the voltage across the diode 0 only. It cannot make it a voltage of a positive voltage. It cannot make the diode voltage, positive voltage any longer. So in the rest of the entire operation, the diode will not conduct anymore. So this is what you should understand now. So only this much it has conducted, only in this duration it has conducted and charged the capacitor up to some level which is plus 15, which is it is 15 volts with polarities like this, and from now on the diode becomes off. So what would be the voltage V0 after this instant? Following this instant, the voltage V0 would be this voltage and this voltage added together. So this is Vi minus 15 volts. So if you look from this direction, Vi minus 15 volts. So whatever Vi is, that would be replicated at V0, but it would be clamped to a level of minus 15 volts. So this level of 0 which was there in the input side now goes to minus 15 in the output side. This is 0, so this is suppose minus 15, this is minus 20. So we are riding on this minus 15 volts. Minus 15 plus 20, some plus 5 range is there. It would go till plus 5. Here it will come to 0. How far it will go? It will go till 35, 20 minus 15. Till here it will go. So this is the way it will behave. So this input and output is not in the same scale, as you can understand, because this has got elongated. Only because I have taken this much as 20 in the input side and 20 in the output side is much longer than this. So these are not in scale. But you get the idea what is happening. So what is happening is the input side voltage is getting clamped to some DC level in the output. So that is called the clamper circuit. So with this understanding of rectifiers, clippers and clampers, most of the diode circuits can be solved. You get the idea how to go ahead. First thing you need to note is when the diode is getting forward biased and when it is getting reverse biased. When there is a capacitor in the circuit, you need to be careful, because the diode may not come to forward bias region for the remaining cycle of operation after the capacitor gets charged. So once the capacitor gets charged, the diode may not at all come to conducting stage anymore. Okay, and then you have to make it off for the remaining analysis and understand how the circuit is behaving after that. So this is what you should keep in mind. So be careful, look at the circuit, understand what is there in the circuit. Is it only diode and resistances? Is there a capacitor? So this thing you first identify, then you slowly progress, try to understand in which region of the input voltage the diode would be forward biased, in which it is reverse biased, and when it is forward biased, some type of output. When it is reverse bias, some other type of output. When there is a capacitor, then the capacitor will get charged, and after it gets charged, the diode may not come to conducting stage anymore, and the rest of the analysis has to follow with the charged capacitor, with the voltage across the capacitor being considered in the circuit. And we have to consider that once the capacitor gets charged, it does not discharge, because the discharging path has a very high time constant because of the presence of the load resistance. So only one thing, we have not mentioned the value of these RLs, but we must be very sure that this RL is very high, in the range of kilo ohms. That we need to be very sure. Also another thing, that the charging happens instantaneously, because the charging circuit, we have neglected the resistance of the diode, which is actually very small. The AC resistance, we have seen that it is very small. So the charging happens almost instantaneously, that we can consider. So the charging happens instantaneously and the discharging never happens. So these two considerations we can have when we are dealing with circuits with capacitances, diode circuits with capacitances. Of course, why we are making these assumptions, how long they are valid, these things has to be kept in the back of your mind. In any situation, if you see that there is a very high resistance with the diode here, then of course a red flag should rise in your head, because the capacitor would not get charged instantaneously. If you see a very low resistance here, then the capacitor will get discharged very rapidly. So these things should be kept in the back of your mind. But all in all, those circuits are normally not given for analysis also, because they are not useful for any practical purpose. So only useful circuits which give some practical application will be asked for analysis. However, those scenarios can also occur, and you should keep those things at the back of your mind. So with this, I would end today's lecture, and in the next lecture I will go into some more special circuits of the diodes. There are some voltage multiplier circuits, and with that I will end the diode section of this course. And a lot of diode circuits you will analyze on your own. Go into the books, refer any additional materials, try to solve diode circuits, look into the solved examples first, then try your hand. Tutorials will also come, and get enough practice for solving the diode circuits. Then everything will be very easy for you. So with this, I would end the lecture. If there is no quick questions or anything, then I would end the recording also, and you would end the meeting as well. Okay, thank you then. Yeah, okay, thank you everyone.